Okay. Now we had a little technical difficulty last time, so I missed some of the slide material, and I'm going to just sort of insert that right now before we go back to the stream of the last lecture. Sorry for the discontinuity, but these things happen from time to time. So we did regular expressions. Last time I started looking at implementation of them. Let's just take a step back and look at, first of all, go back to the world of description, back to the world of specification, and look at how I was preparing when I was redoing the lectures for this cycle, that it might be nice to introduce one of our notations a bit earlier than before. So here it is. We have a Backus-Nauer form. At some point that was called, in some books it's called Backus normal form, but it's not. Backus was the fellow you may remember who did Fortran. He was also involved in the development of Algol 60, or in the definition of Algol 60, and Peter Nauer was the fellow who edited the Algol 60 report, which has this form. Some symbol on the left, which is called for languages, so that is sets of strings. Okay, so a set of strings on the A, and then on the right is a sequence of symbols, which can be either literal characters or strings, such as the literal character A, or they can be another non-terminal symbol, some of which refer to just single characters, which have the same meaning as they do in regular expressions. Namely, the character A stands for the language consisting of just the string A. Saying that some of these strings, or one way to form a string in the language of A, the language denoted by A, is to concatenate one string again, and you concatenate one string from each, and that gives you a string in A. Okay? And so you see, so this is notation. It's very simple. It's a very simple notation. A generalization of this notation, there is a generalization of this notation where the left side can also be a string of symbols, just like the right side. The left side and the right side look the same, and it means if you have a sequence of symbols such as on the left, then you can convert them into a sequence of symbols on the right. And that form is in fact Turing complete. You can do anything with it. This one you can't do anything with this, but it has the advantage that you can do an awful lot, and these forms can be effectively implemented fairly efficiently. Okay, so this is, you'll see this in many different forms. You'll see the colon as the classical symbol for the colon was colon, colon equals. There are also left arrows, right arrows, all kinds of things. But I'm using colon because that happens to be what our tools use, so that's pretty good. All right. Now you can do the usual abbreviation forms. For example, if you instead of writing a whole bunch of rules, one for each right-hand side, you can collect all the right-hand sides together with or, just as you can with regular expressions. You can parenthesize things, and terminal that stands for this, that stands for R, and then sticking that in place of it. So it's the same. It's just a rewrite. There's no essential new power being introduced here. And you can have character classes and so forth. Usually one of the what? What's that? Incomplete thought there. And in fact, in our tool, we'll have even more. We'll also allow you to do the extended forms, such as with regular expressions, plus, times, and so forth. So now one little thing for those of you who are mathematicians, and language lawyers and that kind of thing, you'll look at this definition, you say, wait a minute, he said one way to form a string in A is blah, blah, blah. Well, that can't be the only way because there can be several rules. So can I throw anything else into that set that I want? And the answer is supposed to be no, no, no. You have to only include things that are included in the rules. And so you'll see these statements sometimes that look kind of mysterious until you see this problem that say the language defined by this is the minimal language that meets all these rules. Okay, so that's just a minor technicality, and probably a technicality means something that you probably figured out, that you probably assumed anyway, but we didn't say it, and so a mathematician says that you haven't specified it. All right. Then, of course, if I'm writing this thing to define a language, I've got all these non-terminal symbols, each one of which describes a language. So what am I talking about? Well, we usually pick out one of them and we say, well, actually the purpose of this whole grammar is to define this one symbol. That's the language that we're really interested in. Okay, so those are just a few things. So we have a start symbol, we have a bunch of symbols that define the language, and this gives us a new notation for defining languages. But I'm going to put a restriction for now. So for the purposes of this first unit of the course where we're talking about lexical analysis, I'm going to say we're going to limit these rules as follows. So first of all, I'm only going to I'll allow you to use a non-terminal symbol in this rule. So one of those alphas can be an A, only if it's been defined before all of these rules. So if I can use a symbol B in there as long as all the B rules have occurred before the A rules. Or, and there's one exception, with the one exception that the last symbol, alpha n, the last symbol, I'll allow that to be A. And I'll allow that to be A, but that's it. That's the only thing I can do. So this is what's known as this is one formulation for the type 0. I'm sorry, that should not be type 0, that should be type 3. For the type 3 or regular grammars, sorry, type 0 is Turing complete. This is not Turing complete. Type 3, these are the regular grammars, and they define, and the languages they define, the sets of strings they define are called regular sets. Regular sets of strings. Just terminology, nothing special about that. And it turns out that, and you can convince yourself, I think I'm going to put this on the next homework, you can convince yourself that in fact the languages that I can recognize with this grammar are exactly the same as the ones I can do with regular expressions. Well, actually, I think we might just demonstrate that here. I'll show you how to do it. Take your regular expression R, and take each parenthesized expression in it, and use the expansion that I showed before. Just take all the parenthesized expressions, and make them into new rules. And then the only thing that's left that's strange are the constructs for x star, x plus, and x question mark. Those are the extended regular expression rules. And those are easy, too. So, I mean, for example, I have this construct R star. How could I turn to where R is some symbol, right? So how can I turn that? What can I do to that symbol to define? What can I do to define R star using the restricted grammar that I showed before? Any takers? Suggestions? I have one suggestion, two suggestions. One suggestion, two suggestions. You know, that's too small a percentage. All right, well, fine. We'll start over here.
Your backup scenario
Uh-huh.
the pattern itself,
Uh-huh.
or the pattern followed by R.
Okay, yeah, that's the rule will be named Q. So we replaced R star with just the plain non-terminal Q, and the question is, how do we define Q? And you're saying, okay, so I can have Q be empty, I can have it be R, and I can have,
or you can have it be QR.
Or QR. Okay. Yeah, that works. Any comments on that? So the 3 rules, he said, change this into 3 rules. Change the R star into a Q, and put in 3 rules for Q, which will be, presumably they'll go before whatever rule contained the R star. 3 rules for Q, which will be Q goes to nothing, Q goes to R, and Q goes to QR. Yeah.
Would that be RQ?
Right, RQ, okay, good. Because Q only goes at the end. Anything else? Any other comments? How about you?
With the second rule about having QBR be redundant?
Right, because Q can be empty, therefore RQ will, among other things, give you just a single R. Like this. Okay. So right, that works. So I can do that. Now that must make, I'll bet that makes R plus pretty easy. It is. It matches. Yeah, that's right. It matches R by just having Q. The second Q matches empty. You notice, of course, that this is. So this makes it, of course, a. Stop pointing at the screen. This makes it, of course, a recursive definition. But that's okay. We know how to deal with that. That's what 61A was all about, right? Actually, that's always been kind of strange about 61A. They assume that you know it even before you enter 61A. That's, yeah, we expect a lot of our high schools around here. Okay, so R plus? Any takers? Sure. Right, so this is, it's almost the same except that we don't allow it to be empty. And that means R question mark. R question mark. Okay. Yeah. Yep. So there we are. We can express all of the regular expression things in this language as well. And so there you go. All right. So this is an alternative way of describing the same things. And it turns out that we can show that we can actually get an alternative proof for the finite automata construction that I started last time, just using this. But what this shows is any regular expression can be converted into one of these things. Now, the interesting question is, can you go the other way and show that any language like this can be converted back into a regular expression? I'm going to leave that for the reader. That's actually a bit tricky, but it can be done. Yes?
Is there a symbol for the entity language, or for example, for using with the abbreviation of the or?
For the empty language.
So if we were to use the pipeline
Uh-huh.
abbreviation with R star, how would we write?
Oh, I see. For example, the first one would be Q colon pipeline or bar RQ. Okay, so well, I don't like to do this because it can't be seen by the screencasting folks, so I will speak as I'm doing this. Q goes to bar RQ. And you can see the empty string. I'm sorry, did I do that too small? Okay, that's, yeah, maybe the empty string is a little small here. Yes, it's between. An easy thing to do is to accidentally insert is to put each of the possible options on a new line, starting with a bar to separate them. It means that you've introduced an extra rule, creating the empty string, which you didn't want to do. So, right. So that's anyway. That's that's what you do. It's in fact, I have a little convention when I use my tools. I admit that this is sufficiently obscure or hard to see that I usually throw a comment in. It says /* empty / or something like that, just so that the reader can see that I really mean an empty thing. Right form, and then we take the final rule, and we can expand that by turning the Q3 into. Well, here I've used epsilon. You can't do that in ASCII because epsilon is not in the first section in the 7-bit characters. So, but on the screen I can do anything. Okay, so we have Q3 is either empty or Q1, and Q4 is Q2 followed by Q4 or a single Q2. So that's an example, and you see bar abbreviation, but that's okay. So the final one is in the pure form, and you can do that for any regular expression. As I say, the interesting question is going backwards and finding a. Okay, that clear enough? So this was an introduction, basically, to BNF. BNF with a big ball and chain on one of its legs. And we'll see in the next unit of the course that, in fact, this is a significant restriction. Go back to DFA. So let's just quickly look at the thing we did before. Okay. So first of all, I asked, what does this is a you notice this one is a non-deterministic finite automata. Well, how do we know? And it is not determined. I'm sorry, since deterministic finite automata are subset of non-deterministic finite automata, I have to say this is not a deterministic finite automaton. Why is it not a deterministic finite automaton? Let's see, whom have I not called? Yeah.
Because A can go to 2 different things.
Right. So A at on the very first state, all the other states are fine, but the first state, A can go either back to the original. Can take us back to the original state, or it can move on to the next state. So that's non-deterministic. What do you have to do to make first of all, what does this, okay, so what does this recognize? I have one set over here in the side here, yeah. Right, A, B, C, D, A, B, D, yeah, right. Any string that ends in that long string of random characters. So this would be something like a pattern match, that with ABCD, ABD, $, something like that in Python notation or Perl or Java notation. By the way, there was I saw a question on the notice board that kind of surprised me. Did all of you do Java patterns in 61B or at some point? Did anyone not use patterns in Java? I will have to. Sorry, I should have checked first. Yeah. Listen, this pattern stuff, it just shows up all over the place. So I mean, you'll run into it no matter what you do if you ever deal with text. And you still do have to deal with text occasionally. So if I might just make a professional suggestion, never mind this course, which also asks you to do it, this is good stuff to review. So the Java pattern stuff, for example, or the Perl regular expressions is the same stuff. Those are just good general things to know in your programmer's toolkit. Okay, does this light up in front interfere with seeing the board? Because we seem to have somewhat of a cleft stick here. Either I can make the front row's notebooks more obscure, or I can make the screen more obscure. And I'm not sure which one I want. Okay, well you can give me feedback later. All right, so DFA. I think I've blathered long enough that you've had some time to think about this. How would you do a deterministic finite automaton to recognize this thing? We have one hand, two hands. How about, I don't think I've called on you yet, so what do you suggest?
Well, we would just have to go to the initial state.
Okay.
And the B state, A, B, and D through D and back to the first state. And anytime you do not follow the link that's already on the
It's already there, yeah.
then you link back to the initial state.
Okay, well, that's almost correct. There is a slight problem. So his suggestion is basically this. If I'm on any one of these states, let's see, get the little hand here. If I'm on any one of these states, and for example, if I'm here and I don't see a C, then I'll go back to the beginning. That's almost correct, but there's a little problem with it. Yeah. Right. So in other words, if I'm on any state, say, for example, if I'm on this state, and instead of seeing a B, I see an A, well, that means that I could be at the end of the string and about to see this long string of characters. So I should, in fact, when I see an A, I should go back to this one. And when I see an A here, I should also go back to this one. But if I see anything else, I come back, anything else other than C, I would come back to the initial state. Okay, that's good. And you could imagine repeating that pattern, almost. But let's consider, for example. Right. Okay. So you can imagine repeating that pattern. Suppose that I'm on this state right here. See, so the second B state. So what should my transitions be from that one? So there's the one. So A would take me back to here. D would take me here. Anything else? Everything else takes me back to the initial state? Yeah.
Would C take it back to
Yeah, it would take me back to C would take me back to the C state. So it isn't. So what we get is something. So anyway, it's something that ends in that, and what we get is something that looks like this. A rather complicated thing, where. Oh, I see. I forgot. I left off a couple of the labels. Where there isn't a label, it's supposed to mean and everything else. But I see that I missed a label here. This back edge here should be A. But anyway, you get something like looks like this. It's a considerably more complicated machine than the original one, although its complication is that it has additional edges. Now, it turns out that one can also come up with machines. For example, if we go back to this example, if I had a more complicated thing, like for example, bit strings whose length is divisible by 2, 3, or 5, you'd find that if you work that one out, you'll find that the deterministic machine has quite a few states. In fact, it has 30 states, whereas the non-deterministic machine has fewer states. So non-deterministic machines in general can have fewer states. This wasn't an example, but a real example would probably fill up the screen too much. They can have fewer states and they can have fewer edges. So in general, non-deterministic finite state machines are in fact simpler. Okay, so so at this point, I think it would be a reasonable time to take having gone over that material that we've gone over before, this would be a reasonable time to take a break after I ask for additional questions. Questions? Okay, fine. Let's wait for a few minutes then. One more minute. All right. Let us recommence. So these next few slides were in the readings, so I'll just go over them quickly because they're review. And the idea here is going back to these finite automata to show how you can use these finite automata to recognize any regular expression. And therefore, the finite automata are actually a kind of an implementation. Well, if we could get a computer program to do what the finite automata does, they're an implementation of regular expressions. And the motivation here is, well, finite automata look like the sorts of things that ought to be easy to get a program to mimic. After all, finite state machines are actually used as models of digital circuitry, or some kinds of digital circuitry. So, like computers, for example. So we ought to be able to do that. And this was the construction that's the classical construction of basic regular expressions into finite automata. So the epsilon, for example, is really trivial. You just say the start state is the final state, and there you are. If you run the empty string through this particular automaton, you'll end up in the final state. You will indeed end up in the final state. Everything's great. Single character, you just have one transition on that character. And so if you look at this, if you give it the string A, it will indeed end up in a final state. If you give it anything else, it will eventually blow up. It'll fall apart. There will be a point where it cannot make a transition. You want a concatenation, trivial. You just glue the two machines together. This diagram is sort of is basically a recursive algorithm in diagrammatic form. So in order to concatenate R1 and R2, we assume that you can build the two machines, the R1 machine and the R2 machine. We assume recursively that you can do that, and then I say, okay, assuming that you do that, this is how I handle it. And we also make a few provisions. There's a provision that the resulting machine will have a single start state and a single end state. That's easy enough to arrange. And so this is how we get a concatenation. So if I put a string from R1 that matches R1 into this machine, it will get into the middle state. It will find its way to the middle state here, which happens to be the start state for the second machine. And then if I put a string for R2 in here, it will find its way to the final state. So this will recognize anything in R1 and R2. And if you put anything else in, try to get it to recognize anything else, then either it will blow up inside the R1 part, or it will blow up inside the R2 part, or both. Or also simple, this shows the power of epsilons to isolate pieces of the machine from each other. So I can simply add a start state and a new start state and a new end state, and have it choose non-deterministically which one to try, R1 or R2. And remember, the definition of non-deterministic automata is that if any path through the machine works, then you recognize this, ends up in a final state, then you recognize the string. So the fact that I might choose incorrectly is irrelevant, because if I can choose, if there is a correct choice, then by definition I will recognize the string. And finally, R star, which is the last classical basic regular expression, is equally easy. You just have this, we just take the R machine and we give a back edge so as to get the looping business. And we also allow at any time when you've gotten 0 or more of these matches and are back in the start state of R, at any time you can jump to the final state. And so you put anything that's a concatenation of R's together, and this machine will be able to recognize it by simply going through R and then back to the beginning that number of times, however many times it is, and then jumping to this final state. So there will be a path for any concatenation of R's. And if you give anything else, then at some point you'll be in the middle of R here, and you will blow up because you'll get something that isn't recognizable as a string. Okay. Okay, is that all clear? Yes?
Simple question. Can you make the first state of our final state?
Can I make the first state a final state? Yeah, but that's kind of, well, If I did that, I would then have two final states in the machine.
Without the second.
Or without the second one. I think that that's an interesting question. Well, let me see. I'll have to think about whether I believe that will actually work. Probably will. There are some technical reasons why this is the classic. This is sort of the classical construction. As far as I know, it will work. But sometime I'm going to go back and figure out exactly why they chose to do it this way. I think there were certain things about guaranteeing, for example, that oh yes, I remember what it is. This particular construct, which is taken from the Aho-Setti and Ullman book, by the way, they wanted a machine. They wanted to end up with a machine that had the property that there were only a certain number of a fixed maximum number of arrows coming into or out of any one node, and for some reason I forget it at the moment why exactly they did that. And so if you can make the first state here a final state, and that will work, except that then you can have an unlimited number of things going into and out of the machine, which might affect the implementation somewhat. But yes, that works too. There are various variations, and in fact, one of the things you'll notice is that the machines that you get out of out of this particular construction is by no means optimal. Now, these are just questions for you, and to make sure that they're nice review questions. You can go back and make sure that you understand how to do these things, and if you do before the test, and that will be an indication that you actually understand the construction. So this is basically basically the question here is how can I translate some of these other forms? I can obviously do it by simply converting them first of all to the basic regular expressions and then going and doing the construction. Or you can ask yourself, well, is there a more direct way to do this? So I will leave that to you to think about this a little bit. Except for the first one. That one we can answer right here. How would you do the empty language? So a language that doesn't contain any strings. Any? Sure. Yes. The start state is the final state, but that's epsilon. That gives me epsilon, which does contain a string, namely the empty string. Let's see. How about in the back there? Yeah, anything that doesn't have a final state will not recognize anything. So that will be the empty language. Totally useless, of course, but if you're doing mathematical constructions, sometimes that's useful. Okay, so here we have an example. I have AB star or C, the quantity star. You'll recognize immediately that that's redundant. I could get rid of the first star, but I'm not going to do that. I'm just going to do this construction. So again, what we do is we break this down recursively. So you say, okay, well, this regular expression consists of this inner expression, AB star or C starred. So the first thing we should do is construct the regular expression for AB star or C. AB star or C consists of AB star ORed with C. Therefore, the first thing we should do is construct the regular expression for C and the regular expression for AB star, and then put them together, and so forth. So if we do this, when we get down to the basis of the recursion, the endpoint of the recursion will be the regular expressions it would be the regular expression for A, for B, and for C. Those would be the final points of the recursion. If we take that a little farther, then we would get the concatenations of those. So we would get these two machines here. The first one is actually concatenation of two machines, the A machine and the B machine. The third one is the C. So so the recursion eventually gets us to this point. So now the next thing we have to do is to make this AB thing into a star. So we apply the star construction, and that gives us this. You notice I'm not marking final states yet because we haven't gotten to the end. Then we now have an AB star and a C, so we apply the OR construction to put them together, and that gives us this. And then finally we want this to be we want the whole thing to be starred, so we put in the star construction, and that gives us this finally. And now I add the final state, and everything's done. So that's kind of cute. Well, that's how it works. And you'll notice that this is a horrendous machine. I mean, we've got epsilons all out the wazoo. And if you think about it, well, this is kind of silly, really. I mean, so I have an epsilon transition to here, and then the only thing it can do is epsilon transition to here, and then the only thing that can do is epsilon transition to back there. So why the heck didn't I just transition to here in the first place? Well, it's a good question. Okay. But that's what happens when in fact, this is an excellent example. The algorithm that built this machine is easy to understand and simple. And you just know that this algorithm works. Now, the result is a horrendous machine from an efficiency point of view. But we could imagine, but we know it's correct. So now we can do something else. Maybe there's another easy to understand procedure which will take one of these horrendous machines, regardless of how it was constructed, and convert it into a better machine. And this sort of layering of or modularization, do a simple construction, keep things simple at each stage, focus on improving one thing or getting one thing right. That's exactly what you see in an optimizing compiler. So you have a code generator that generates naive code, and then you have something that improves it without having to know exactly how to generate the naive code. So now how do we implement these things? Well, let's go back to one of the two. So we have a machine where you can you go through a bunch of states, and you can at any point jump back. At any point jump to multiple states. We could program that directly. We could keep around something that keeps track of that. But if we and we would get something that looks like this, that would keep track of the fact that we have states 0, 1, and 4. You can be in state 0, and you can jump to states 1 and 4 at the beginning. Then after seeing an X, you can be in either state 2 or 5, and so forth. And the idea is, so the red states indicate where you can be after any number of characters. And so the insight is, okay, at each stage, all I have to know is what set of possible states could I be in. And that tells me what the next set of possible states I can be in. Idea, there are only a finite number of possible sets of states, so let's make those the states. And this is what you get, a completely deterministic machine that recognizes the same thing. Well, we have to stop here. So I will, and we will get back to this. We'll finish up the one or two slides at the end and go on to the next topic.